Hey mathematicians, we're checking out 6.2 stationary points. It's out of 16C in the text. A stationary point is not like paper stationary, it means stopped stationary. So it's not moving, the point's not moving. They say it's when f prime of x is 0, and we'll talk about why that is and what it means. But this is the official jargon. When I think about stationary, I think about not moving, right? It's something not moving, which I don't generally do, but so not moving, it means that if this point is not moving up or not moving down, it means its tangent is zero, the slope is 0, right? Its tangent is 0. It's not cruising up like this point is going uphill, so its tangent is up. This point is going downhill, so its tangent's down. This one is doing neither, it's parked. So the tangent is horizontal, means its derivative is 0, and even if it's not a local maximum or local minimum, it's still going to have a 0 slope if it's at one of these what they call a stationary inflection point. Its derivative is 0, so when f of x equals 0. So that's kind of logically why I see that being the case. Let's look at that with Desmos. So get your head out of the way, G. I'm still here. So this is f of x is x cubed. That's this curve. And if you watch the dot cruise up, the dotted line shows you the slope, and you can see the slope getting lower and lower and lower. It gets the curve gets less and less steep, right? And eventually it sort of parks itself, and you can see the orange line shows you the actual slope. So here the slope of the green line is, the green dotted line is 2. Right? It starts up here where it's high slope and gets less and less steep, less and less steep, less and less steep, and eventually the slope is 0 at this stationary inflection point. It's not a local maximum or minimum because eventually it keeps going uphill, so it never switches signs, right? And so if you ran this, right, you never see the orange line go into the x is negative or the y is negative area. Cool. Likewise, if we made this whole thing negative, that, bam, and we flipped it around like that, you can see that the tangent here is negative. It's going downhill, downhill, downhill. It pauses at its stationary inflection point and then continues to go downhill. Cool. So when that derivative is 0, you have the stationary point. The point itself is not moving up or down, it's moving horizontally. And you can see it moving horizontally. The tangent only becomes negative once it starts moving downhill. Right? So it's going downhill, and right in here, not much movement downhill. Same sort of thing happens if you're talking about x squared, not x to the 32. Thank you, though. You're going downhill, 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 and so right now we have a negative tangent, right? That's why the orange is in the negative area. Once we get to 0, we get a 0 tangent, and you can see that mostly it's just going horizontally here, so it has no real slope. And that's why the orange line is hovering around 0, because its slope is pretty close to 0 right in here. And if we zoomed in, it would be even more apparent. And then as we cruise out of there, now it goes positive. Right? So if you played this, you see orange in the negative on one side, negative, 0, positive, and it switches signs. And that's why you can tell it's a local minimum. If we made this whole thing negative, flip over and we do the same thing, but our tangent starts as positive, it's going uphill, but it's getting less and less steep. Eventually the slope comes to 0, and then so it's not moving up or down in this spot very much, and then it falls off, and now the slope's negative. So you could see in here a 0 with sign changes on either side, and that's what this piece is about. Alright, I'm back. That's what this piece is about. Well, here, let's look at it on this side. With a local maximum, the slope here was positive, we go to a stationary point, and on the other side the slope is negative. So it goes positive and then negative around the stationary point, and that's indicative of a local maximum. And in the opposite, this is why I'm not an English teacher. Conversely, there it is. I've only had 6 cups of coffee. Conversely, this has negative slope here, negative slope, goes to a stationary point, a 0, right here, and then it goes to a positive. So negative, stationary point, positive, indicative of a local minimum. And when it doesn't change signs, when it's going uphill, positive, right, stationary point, and then keeps going positive, that's what we call a stationary inflection point. So here's a little summary of that. If you were looking at a shape like this, you'd have positive slope here, a 0 slope there, and negative there. So your sign diagram would look like positive on one side, negative on the other. And that's indicative of a local maximum. So hopefully you can see one of these and understand the other ones. Same thing here. If you're looking at a right side up parabola, an up opening parabola, on one side it has negative slope, the 0, and on the other side it has a positive slope, negative, positive around the 0. That's a local minimum, right? Because it's going downhill to it, hits it, and then goes uphill. It's got to be a minimum. And then on this side, if your diagram looks like that, this is an x cubed or something like that. This is a positive and positive around a 0, right? And so your sign diagram would look like that, or possibly the other way around, negative and negative, and they look like that, right? So same signs gives you a stationary inflection point. It's going the same way the whole time. It just pauses. Cool. All right, so let's try to find those with calculus. Calculus, damaging averages since 1845. Long before that, my friend, long before that. So classify all the stationary points. So they want to know if they're maxima, minima, or stationary inflection. Okay, well, let's find those. Here's the original equation. And so we want to talk about how the point is changing. So we use some calculus on it to find its derivatives, right? So you find this. If you clean this up a little, we want to find when the derivative is 0. That's where it pauses. So if there's lots of ways to find the zeros, whatever you're comfortable with, I'd probably just factor it. And if you factored this more fully, it would look like that. You set it equal to 0, and so its zeros are at 3 and negative 1. Cool. And so you have this sign diagram with 3 and negative 1, and you've got to figure out where the sign is, or where the values are on either side. So you'd pick a number between 1 and 3, and so let's pick 0. You'd throw 0 into here. So you'd say 0 minus 3, 0, so you'd say negative 3 times a positive, this whole thing would be negative. And so in here, between here and here, we know this is negative, right? Pick a number that's bigger than 3. Let's try, I don't know, 4. And if you plugged 4 in, so we're going to test a point on this side. We're going to plug in 4. So this would be 4, and this would be 4. This would be positive, 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 right? It doesn't even matter what the number is. So that means this is positive on this side of 3. Great. And then we do the same thing for negative 1. So let's pick, I don't know, something like negative 2, right? And see what happens here. So you go negative 2, negative 2. This is negative, this is negative, this is positive, so the whole thing should be negative times a negative should be a positive. So on this side, it's positive, bing, and we've built sort of a sign diagram. And so the red line is what the curve looks like. But you know that at these points, at the zeros that we found, this stops moving up or down. It's an inflection point, it's a stationary point. And so with this one, this is going from here, before the inflection, before the stationary point, it's going uphill, uphill, uphill. It stops, and now it's going downhill, downhill, downhill. We know because of this is going uphill, now it's going downhill. It must be a local maximum, right? And then same thing, it's going downhill, downhill, downhill till it gets to the 0. It stops, and then it starts going uphill, local minimum, right? So we know that at 1 has to be a max just because of the sign change, and 3 has to be a min because of the sign change, right? Or you can graph it, but if you don't have, if this is a non-calculator piece, this is a kind of a quick way to do it. So we have a local maximum when x is -1, and you plug that back into the original equation, and you get 10. Cool. So your local maximum is 1, 10, and it should look like that, right? Same sort of thing here. Your local minimum is at 3, so throw 3 back into here. Into the original equation, you get -22. So the other one should be -22. So there we go. We found and classified all our stationary points. We found local maxima and local minima, but no inflection points. Fine. This is the same sort of idea. So it's, if you're a little fuzzy, walk through this again with me. But if you're like, I got it, then move on. So we want to find the greatest and least value. They're being sneaky. They give you an interval. So it might be that between -2 and 5, it's doing something like this. Well, I bet it's doing something like this. It's going up, going down, and going to here. And so I bet that the maximum will be one value, and the minimum will be the end of the road. You know what I'm saying? Like, not this local minimum will still not be as low as this end point. That's my guess. That's what I've seen before. And I guess I put this together, so I should have seen that. Let's try that. So we're taking the derivative. Here's the derivative of this guy. And if you factor that or solve, we want to find the zeros, so solve it however you like. It looks like zeros should be at 0 and at 4. Yeah, 0 and 4. Great. If you built a sign diagram for that, you'd say, I got zeros at 0 and 4. Get rid of that. So that's where these are. Let's do them in black. 0 and 4. Let's see the values of the derivative of the slope between there. And I'm trying to like show that these are true because we don't know them implicitly. So let's pick a number between 0 and 4. Let's pick 1 and see what happens. So this is 1 times 3. So this is positive when we put 1 in here. And this is negative when we put 1 in here. So 3 times 1 positive times negative should give you a negative. So that's why this piece is a negative. Now we don't necessarily know that it switches. Often it does, but if it doesn't switch, then it's a stationary inflection point. So let's test a number on this side, like, I don't know, 5. So this would be 3 times 5 and 5 minus 4. This is positive, so this should be positive over here. Likewise, if we pick a number over here, -1, this should be 3 times -1. This should be negative, and this should also be negative. So negative times negative gives you this positive. All right, so that's what our sign diagram looks like. We don't know these little loopies, but we do know that if it's going uphill here and downhill after the 0, this must be a max. Ooh, I got the large chunky one. Now it's going downhill on this side, and it's going uphill on this side of the 0, so this must be a minimum. Okay, so we'll test those maxima and minima in the same way. We're going to plug in 0 and 4, and if we plug in 0, let's see, did they do 0 first? Oh, we're plugging in an endpoint, right? Plug in this endpoint like we were looking at, but plug it back into the original equation. If you plug -2 in, you should get -27. You get -8 and 4 times -20. Yeah, okay. So you plug this back into here, you get this value. You plug in each of our zero points. So you plug in this local max back into here, and if you plug it in here, 0 and 0, these are all canceled out, and you're left with 5, just like we'd expect. Plug in your local minimum. You should get -27 if you do the calculations correctly, and then you plug in the endpoint 5, just because it might be the case that it's bigger or smaller. So it's asking us for the greatest value Well, the local maximum, that one's the greatest value. And the smallest value is one of these negative 27s. All right, so if you graph that, it would look like this. And you can see that here's our local maximum that we found with this. And this local minimum has the same value as this endpoint. So they're both the same, the least value is negative 27. And we've sort of classified the points. This is the local minimum, but it doesn't necessarily have to be the only lowest point, right? If we picked a wider window, if we kept going a little bit, this would, and we said between to negative 3, then negative 3 would have been the smallest, whatever y value is associated. Cool. All right, there you go. Stationary points. See you later.